Welcome again. We have been discussing the convolution sum that is used to characterize a discrete time LTI system in terms of its impulse response. Now, like in the continuous time case, there are some properties of discrete. Actually, these are the properties of convolution sum. जैसे उस time भी हमने कहा था कि first, the sum itself has some properties like commutative, associative, distributive. Then जो हमारे system properties है causality and stability, we can express those properties in terms of convolution sum, actually in terms of the impulse response, right? So the properties are similar as far as the sum is concerned. So let me generally put out that it's properties of discrete time LTI system, right? So first property is for the operation itself, that it is commutative, right? Which means the sum itself, that is y of n, it is x of n convolved with h of n. You can also express it the other way around, h of n convolved with x of n. You can easily prove it, I'm sure. Last time हमने किया था. You just make some substitutions, so that is a arithmetic thing. I hope you can do it. So in terms of summation, it will be summation k runs from minus infinity to infinity, x of k, h of n minus k. Fine. So this is the same thing as computing this sum. K is equal to minus infinity to plus infinity, h of k, x of n minus k. Okay. So you can perform those folding and shifting operation on h of n. Yeah, you can perform it on x of n, depending upon कि आपका कौन सा sequence is feasible to those operations. It's just a choice. ठीक है. Then we have the associative property, which states that if you have convolution like this, it is always equivalent to this thing. So it is associative in nature. Fine. Then again, it is distributive over addition, so which means that if I have a convolution operation defined over, say, sum of two sequences like this, h1n plus h2n, you can distribute this operation over the summation. Okay, so mathematically it means like this: h1n plus x2, sorry, not x2, x of n convolved with h2n. So it is distributive over addition. Okay, so these are the properties of the operation itself. Next, we'll be interested in the system properties expressed in terms of this convolution sum, which will later boil down to the impulse response. So, like we did in continuous time case, we'll try to analyze a causality of discrete time LTI system. Okay. So it will be a similar kind of an analysis. We'll just break the sum into two parts, then we will equate 1 to 0 and we'll come up with the result. And you'll see there will be a great similarity between the two results. If you remember, in the continuous time LTI system, we generalized that a continuous time LTI system is causal if its impulse response is 0 for n less than 0, yeah, for t less than 0, right? So So like again we'll start with the जो generalized expression है y of n. It is k is equal to minus infinity to plus infinity h of k x of n minus k, right? Now I can break this summation into two parts. The first part will be from minus infinity to minus 1, which means it will cover my negative time axis like this. And the second part, it will be for the positive time axis, that is extending from 0 to infinity, h of k x of n minus k, like this, right? Then again, if you consider the first summation, the one I put in blue, so let's consider this one. If I expand some of the values, so it will start from minus infinity and then it will have values, negative values, say h of minus 2 x of n plus 2, then h of minus 1 x of n plus 1, fine. And you'll see that this summation, so this part of the summation, it includes future input samples. N plus infinity minus 1, n plus 2, n plus 1, fine. But you know that a causal system, it cannot have dependency on the future input samples. It can only depend upon the current and the previous samples. So this means for causality, I have to ensure that this particular summation, that is this summation k running from minus infinity to minus 1, h of k x of n minus k, it has to be equivalent to 0. Okay. Now generally speaking, it will not be always true कि आपके जो input samples हैं they are 0, because input samples, they will definitely have some value. So this means since this part cannot be equivalent to 0, generalizing it, huh? Maybe sometimes आपका एक आध sample 0 के बराबर है, but you cannot generalize कि आपके input samples हमेशा 0 होंगे. That thing you cannot generalize. So for causality, you have to ensure that h of n is equivalent to 0 for n less than 0. Okay? So an LTI system is causal at discrete time. To be more specific, discrete time LTI system is causal if and only if its impulse response, that's h of n, is equivalent to 0 for n less than 0. Okay. We had a similar kind of generalization for the continuous time LTI system. अब वहाँ पे difference इतना था कि it was defined for a continuum of time. Here we define it for discrete samples of time, right? But physically it is the same thing. Then, which means since we have put this part to 0, तो आपका जो output होगा causal LTI system का. So for a causal discrete time LTI system, my output will be the summation that extends from k is equivalent to 0 to infinity h of k x of n minus k. Again, this will be the output of a causal discrete time LTI system. Fine. So the generalization is a similar one that we got in the continuous time LTI system. Next, we will discuss the stability. Stability, that is bounded input, bounded output stability of a discrete time LTI system. Okay. This maybe you will see it will be a similar kind of relation, similar kind of analysis. So we have y of n extending from k is equivalent to minus infinity to plus infinity, h of k x of n minus k. Then we'll take the magnitude on both sides, y of n equivalent to summation k runs from minus infinity to plus infinity, h of k x of n minus k. Okay. Then you know that the absolute value of the total sum, it is always less than or equal to the sum of the absolute values of the individual terms that exist in the sum. So which means this will be less than equivalent to summation हम बाहर निकालते हैं k is equal to minus infinity to infinity. Take the individual sum. N minus k. Now for stability, we always give a bounded input, that we always provide a system with the input which is bounded. So kind of an assumption that to check the stability, if I am giving a bounded input, which means that the magnitude of the input is bounded by some value, say b subscript x, and it has to be finite, so it will be less than infinity. Okay, so this is the magnitude of our input. So if I apply this thing here, it means जो आपका y of n होगा, it will be, so b of x is bounded to come outside summation k runs from minus infinity to plus infinity h of k. So it all depends upon this summation, and if this summation is finite, we can say that the system is stable. ठीक है, so जो हमारा condition बनता है, तो for y of n to be finite, this summation k runs from minus infinity to infinity h of k, this should be finite, right? Therefore we can say that a discrete time LTI system is stable if and only if, जैसे हमने वहाँ पे एक्सप्रेस किया था continuous time केस में, if and only if its impulse response is absolutely summable. By absolutely summable, I mean that this summation, it should be a finite sum. It should be less than infinity. Okay? So generalizations are same two conditions. They exist for the continuous time LTI system. It's just the way we express it. There was a continuous time case, so it was in terms of an integral. Here this is the discrete time case, so it is in the term of a summation. Okay, so this was all about characterization of the discrete time LTI system. Thanks.